So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're lying in one specific spot, one room, one bed, one particular arrangement of pillows and blankets, and everything about how you got here today followed one particular chain of events. You woke up this morning. You made certain choices. Things happened in a certain order, and all of that led to this exact moment. Simple enough, right? One you, one life, one sequence of events unfolding in one universe. But what if that's not the whole picture? What if, in some sense that physicists actually take seriously, there are other versions of tonight, other arrangements, other outcomes, other paths the universe could have taken, and maybe did take, branching off from every quantum event that's ever occurred since the beginning of time? That's the multiverse. Or at least, that's one version of the multiverse. Because here's the thing, and this is what makes this topic so wonderfully strange. There isn't just one multiverse idea. There are several, and they come from completely different places in physics. And some of them have almost nothing to do with each other. Some come from quantum mechanics. Some come from cosmology. Some come from string theory. And they all point, in their own way, to the possibility that what we call the universe might be just one tiny pocket in something enormously, almost incomprehensibly larger. Now, I want to take you through all of this slowly, really slowly, because the multiverse gets talked about a lot in movies and TV shows and pop science articles, and it usually gets smushed together into one big vague idea about parallel worlds and alternate timelines. And that's fine for entertainment, but the real physics underneath is so much more interesting than that. It's weirder, it's more specific, and honestly, it's more beautiful. So let's start at the very beginning, with the piece of physics that first cracked open the door to this whole conversation. And that means we need to talk about quantum mechanics. Not all of quantum mechanics, just the part that matters for tonight. And it starts with a problem that physicists ran into in the early 20th century. A problem so strange and so stubborn that we're still arguing about what it means more than 100 years later. Picture this. It's the 1920s. Physics is having maybe the most extraordinary decade any science has ever had. In just a few years, a small group of mostly young European physicists, people like Werner Heisenberg, Erwin Schrödinger, Max Born, Niels Bohr, Paul Dirac, are building a completely new theory of how the very small works. They're figuring out the rules that govern atoms and electrons and photons, and the theory they're constructing is quantum mechanics. And it works. It works spectacularly. It predicts the behavior of atoms with stunning precision. It explains the periodic table. It explains why metals conduct electricity. It explains the colors of light that hydrogen emits. The math is gorgeous, and the predictions match experiment after experiment. But there's a problem. A deep, uncomfortable philosophical problem that sits right at the heart of the theory. And the problem is this. The math seems to say that before you measure something, a particle doesn't have a definite state. It's not that you don't know where the electron is. It's that the electron genuinely doesn't have a single location. It exists in what's called a superposition, a kind of smeared-out combination of many possible states all at once. The math describes this beautifully with something called a wave function, a mathematical object that encodes all the different possibilities and their probabilities. Schrödinger wrote down his famous equation in 1926, and it tells you exactly how this wave function evolves over time. Smooth, elegant, deterministic. Given the wave function now, you can calculate what it will be a moment from now with perfect precision. But then you measure the particle. You look to see where the electron actually is. And suddenly, you get one definite answer. The electron is here, not there. The wave function, which a moment ago described this whole spread of possibilities, seems to suddenly collapse down to a single outcome. And here's what's so troubling. Nothing in Schrödinger's equation describes that collapse. The equation says the wave function should keep evolving smoothly. It never says, and now pick one outcome. The collapse is something physicists had to bolt on by hand as a separate rule. When you're not looking, the wave function evolves according to the equation. When you do look, it collapses. That's the standard story, and it's often called the Copenhagen interpretation because it was largely developed by Niels Bohr and his colleagues in Copenhagen. Now, this bothered a lot of people. It bothered Einstein, famously. It bothered Schrödinger himself. That's actually the whole point of his cat thought experiment, which people usually get wrong. Schrödinger wasn't saying, "Isn't it cool that a cat can be alive and dead at the same time?" He was saying, "This is absurd, and something must be wrong with how we're interpreting the theory." The idea that measurement has some special magical role, that consciousness or observation somehow causes the wave function to collapse. It felt ad hoc. It felt like a patch, not an explanation. But for decades, most physicists just kind of shrugged and moved on. The theory worked. The predictions were right. And Bohr, who was enormously influential, essentially told everyone to stop worrying about what the math really meant and just use it to make predictions. Shut up and calculate, as the saying goes. Though that phrase actually came later, and that might have been the end of it, except that in 1957, a young graduate student at Princeton decided he wasn't satisfied with shutting up. His name was Hugh Everett III, and he's one of the most fascinating figures in the history of physics. Everett was working on his PhD under John Archibald Wheeler, who was himself one of the great physicists of the 20th century. Wheeler coined the term black hole, among other things, and Everett had an idea that was breathtaking in its simplicity and absolutely wild in its implications. Here's what Everett said. What if the wave function never collapses? What if Schrödinger's equation is the whole story? It applies all the time, to everything, with no exceptions. No special rule for measurement, no collapse, no magical role for observers. Just one equation, running continuously, governing the entire universe. Think about what that means for a second. If the wave function never collapses, then when you measure an electron that's in a superposition of being in two places, the measurement doesn't force one outcome. Instead, the superposition spreads. It infects the measuring device. It infects you, the observer. The wave function of the whole system, electron plus detector plus you, evolves into a superposition of two branches. In one branch, you saw the electron on the left, and your brain recorded left. In the other branch, you saw the electron on the right, and your brain recorded right. Both outcomes happen. Both versions of you are real. And from the inside, each version of you thinks they got one definite result because each version only has access to their own branch. That's the many worlds interpretation. That's where the multiverse first enters physics, not as science fiction, not as speculation, but as a straightforward reading of the most successful theory in the history of science. Everett wasn't adding anything to quantum mechanics. He was taking something away, the collapse postulate, and following the math wherever it led. And where it led was to a universe that's constantly branching, splitting into vast numbers of parallel realities every time a quantum event occurs. Now, I want you to sit with how radical this is, because it's easy to hear parallel universes and think it sounds like a comic book. But Everett's reasoning is actually incredibly conservative in one sense. He's saying, we have this equation that works perfectly every time we test it. Why do we need an extra rule that we've never observed, the collapse, when the equation by itself already explains what we see? Each branch of the wave function contains observers who see definite outcomes. The math already predicts our experience. We don't need collapse. We just need to take the equation seriously. But of course, taking the equation seriously means accepting that the universe is unimaginably larger than what we can see. Every quantum interaction, and there are trillions upon trillions happening every second in your body alone, potentially creates new branches. The number of branches grows so fast it makes astronomical numbers look quaint. And here's a detail that matters. These branches don't interact with each other after they split. They're like rooms in an infinite hotel where the doors lock behind you. Each branch is, for all practical purposes, its own self-contained world. You can never visit another branch. You can never communicate with your other selves. The branching is real, but it's also utterly invisible from the inside. Everett published his thesis in 1957 in a shortened version that Wheeler helped him edit. The full version, which was more detailed and more ambitious, wasn't widely available for years. And the response from the physics community was, well, it was mostly silence. A few people engaged with it. Bohr's camp dismissed it. Everett himself was deeply disappointed by the reception. He left academia entirely, went into defense analysis and operations research, worked for the Pentagon, made some money, and largely stopped doing physics. He died in 1982 at the age of 51, of a heart attack, having never really gotten the recognition he deserved during his lifetime. His son, Mark Oliver Everett, later became the frontman of the band Eels and has spoken movingly about discovering his father's physics work after his death, about finding boxes of papers in the basement and slowly realizing that his quiet, somewhat distant father had proposed one of the most extraordinary ideas in the history of science. The many worlds interpretation didn't really start gaining serious traction until the 1970s and 80s, when a physicist named Bryce DeWitt championed it and gave it the name many worlds. Everett himself had called it the relative state formulation, which is more technically precise, but much less catchy. DeWitt wrote influential papers and edited a collection that brought Everett's work to a wider audience. And slowly, over the decades, many worlds went from being a fringe idea to one of the most popular interpretations of quantum mechanics among physicists. Not the majority view, necessarily. Surveys of physicists show a pretty even split between several interpretations, but certainly a serious contender, taken seriously by serious people. And here's what I find really interesting about this. The many worlds interpretation doesn't make different predictions from standard quantum mechanics. You can't design an experiment that would tell you whether many worlds is right and Copenhagen is wrong, or vice versa. They agree on every measurable outcome. The difference is entirely about what you think is really happening behind the scenes. Copenhagen says the wave function collapses and only one outcome is real. Many worlds says the wave function never collapses and all outcomes are real. Same predictions, radically different pictures of reality. And that raises a question that's more philosophy than physics. If two theories make identical predictions, is there any way to choose between them? Is one of them true? Some physicists say many worlds is simpler because it has fewer rules, just Schrödinger's equation, nothing else. Others say it's extravagant because it postulates an infinite number of unobservable universes. The debate gets surprisingly heated for something that can't be resolved by experiment, and it touches on deep questions about what a scientific theory is supposed to do. Is it just a tool for making predictions? Or is it supposed to tell us what reality is actually like? We'll come back to that question, because it matters for everything else we're going to talk about tonight. But I want to flag something important before we move on. The many worlds multiverse, the one that comes from quantum mechanics, is just one type of multiverse. And it's actually not the type that most cosmologists are thinking about when they use the word. Because while Everett was puzzling over wave functions in the 1950s, something completely different was happening in cosmology, something that would eventually lead to a very different kind of multiverse, one that has nothing to do with quantum branching and everything to do with the large-scale structure of space itself. And that story starts with a question that sounds almost childishly simple. Why does the universe look the way it does? Why is space so flat, so uniform, so big? Why does the cosmic microwave background, that faint afterglow of the Big Bang, look almost exactly the same temperature in every direction, even in regions of space that should never have been in contact with each other? In the late 1970s, a young physicist at Stanford named Alan Guth was thinking about a completely different problem: magnetic monopoles. These hypothetical particles that should have been produced in huge numbers in the early universe but have never been observed. And in the process of trying to solve that puzzle, he stumbled onto something that would reshape our entire understanding of the first fraction of a second after the Big Bang. Guth was working on grand unified theories. These ambitious attempts to merge three of the four fundamental forces of nature into a single framework. And one prediction of these theories was that the early universe, as it cooled from unimaginable temperatures, should have produced vast quantities of magnetic monopoles. Think of a monopole as a magnet with only one pole, just a north or just a south, without the other end. Classical electromagnetism says that's impossible. You always get both poles together. But these grand unified theories said no. Actually, in the extreme conditions right after the Big Bang, monopoles should have formed everywhere. The problem was, nobody had ever found one. Not a single magnetic monopole, anywhere, ever. And the predicted abundance was so high that they should have been easy to detect. So either the grand unified theories were wrong about monopoles, or something happened in the early universe to dilute them, to spread them out so thin that we'd never stumble across one. And that's where Guth had his insight. It came to him in December of 1979, and if you read his own account of it, he describes staying up late, working through the math, and writing in his notebook, in capital letters, underlined, the words, "spectacular realization," which is a wonderful thing to find in a physicist's personal notes, because it tells you he knew, right in that moment, that he'd found something big. Here's what he realized. If the very early universe went through a brief period of extraordinarily rapid expansion, not the gradual expansion we observe today, but an exponential blow-up, a moment where space itself doubled in size again and again and again in an unimaginably short time, then that would solve the monopole problem beautifully. Any monopoles that had formed would be flung so far apart by this expansion that you'd be lucky to find even one in the entire observable universe. They'd still exist, in principle, but they'd be scattered across such a vast volume of space that they'd be effectively invisible. But here's what's really clever. Guth quickly realized that this same mechanism, this brief burst of exponential expansion, which he called inflation, didn't just solve the monopole problem. It solved the other two big puzzles as well. The flatness problem and the horizon problem, the ones we touched on earlier. Let me walk through why, because this is genuinely elegant. Start with flatness. The geometry of space can be curved, positively curved like the surface of a sphere, negatively curved like a saddle, or flat like a tabletop. And observations tell us that the universe is flat, or very, very close to flat. The trouble is, in standard Big Bang cosmology without inflation, flatness is an unstable condition. It's like balancing a pencil on its tip. Any tiny deviation from perfect flatness in the early universe would have grown over time, so that by now, billions of years later, the universe should be either dramatically curved in one direction or the other. For it to still appear flat today, the initial conditions would have had to be fine-tuned to something like 1 part in 10 to the 60th power. That's a 1 followed by 60 zeros. That level of fine-tuning is deeply uncomfortable for physicists. It feels like cheating. It feels like there should be a reason. And inflation gives you that reason. Imagine you're standing on the surface of a balloon and someone inflates that balloon to an absolutely enormous size, not just big, but cosmically, absurdly, incomprehensibly big. The patch of surface you're standing on, which might have been noticeably curved when the balloon was small, now looks perfectly flat to you. Not because the curvature went away, but because the balloon got so large that any curvature is stretched out beyond what you could ever hope to measure. That's what inflation does to space. It takes whatever geometry the universe started with, curved, lumpy, messy, and stretches it so dramatically that the observable portion looks flat. No fine-tuning required. It just happens naturally. Now the horizon problem. This one's a little subtler, but stay with me. When we look at the cosmic microwave background, that ancient light released about 380,000 years after the Big Bang, we see that it has almost exactly the same temperature in every direction. The variations are tiny, on the order of 1 part in 100,000. And that uniformity is beautiful, but it's also deeply puzzling, because in the standard Big Bang picture, regions of space on opposite sides of the sky were never in causal contact. Light hadn't had time to travel between them. They couldn't have exchanged heat, or information, or anything at all. So how did they end up at the same temperature? It's like walking into a room and finding 1,000 cups of coffee all at exactly the same temperature, even though none of them were ever near each other. You'd think someone must have coordinated that somehow. Inflation solves this by saying they were in contact once. Before inflation happened, the region that would become our entire observable universe was incredibly tiny, smaller than an atom. In some versions of the theory, everything was close together, in thermal equilibrium, all at the same temperature, all able to communicate and exchange energy. Then inflation hit, and that tiny patch was blown up to cosmic proportions in a fraction of a second. The uniformity was already there before the expansion. Inflation just preserved it while making everything enormously bigger. So you have one mechanism, this brief, violent burst of exponential expansion, that simultaneously explains why the universe is flat, why it looks the same in every direction, and why we've never found a magnetic monopole. That's a powerful package. Guth published his paper in 1981, and the response from the physics community was immediate and enthusiastic. Not everyone was convinced, but a lot of people recognized that this was, at the very least, a compelling framework. Now, Guth's original version of inflation had a technical problem. It's sometimes called old inflation, related to how the inflationary period ended. In his model, inflation stopped through a process like a phase transition, similar to water freezing. And it turned out that this transition would happen in separate bubbles that would never merge properly. You'd end up with a universe that was wildly inhomogeneous, full of bubble walls and empty voids, nothing like the smooth universe we actually see. Guth himself recognized this problem almost immediately, and within a year or two, other physicists, most notably Andrei Linde in the Soviet Union, and independently Alan Guth's colleague Paul Steinhardt, along with Andreas Albrecht at the University of Pennsylvania, developed what's called new inflation, or slow-roll inflation, which fixed the graceful exit problem. In their version, the field-driving inflation, called the inflaton field, rolls slowly down a gentle slope in its energy landscape, and inflation ends smoothly everywhere, not in messy bubbles. The details are technical, but the key point is that by the early 1980s, there was a workable version of inflation that solved the big cosmological puzzles without creating new ones. And here's where things start to get really interesting for our multiverse story. Because Andrei Linde, and this is a character worth knowing about, took inflation and pushed it further than anyone else was willing to go. Linde is a Russian-born physicist, eventually based at Stanford, and he has this wonderful combination of mathematical rigor and wild theoretical imagination. In 1983, he proposed something called chaotic inflation, which was a simpler and in many ways more natural version of the theory. And then, building on that, he developed an idea that would become one of the most mind-bending concepts in all of modern cosmology. He called it eternal inflation. Here's the core idea, and I want you to sit with this for a moment because it's strange. In most versions of inflation, the inflaton field, that energy field driving the rapid expansion, eventually decays. It rolls down to a lower energy state. Inflation ends, and the universe transitions into the kind of slower expansion we observe today. The energy stored in the inflaton field gets converted into matter and radiation. That's essentially the Big Bang, the hot, dense state that produces all the particles and light we see. So inflation sets the stage, and then the Big Bang happens as inflation ends. But Linde realized something unsettling. Inflation, once it starts, might not stop everywhere at the same time. In fact, it might not stop everywhere at all. Think about it this way. The inflaton field is a quantum field, which means it's subject to quantum fluctuations, random tiny variations in its value from place to place. In most regions, the field is rolling downhill, losing energy, heading toward the end of inflation. But in some regions, just by random chance, the quantum fluctuations kick the field back uphill. They add energy instead of subtracting it. And in those regions, inflation continues. And because those still inflating regions are expanding exponentially, they're getting bigger incredibly fast. Faster than the regions where inflation has ended. So even though inflation is constantly ending in various places, the regions where it's still going are growing so rapidly that the total volume of inflating space is always increasing. Inflation, once it starts, never completely stops. It's always happening somewhere, and every time inflation does end in a particular region, every time the inflaton field successfully rolls down to a low energy state, that region becomes what you might call a pocket universe, a bubble of post-inflationary space where matter forms, galaxies coalesce, stars ignite, and maybe, just maybe, someone lies awake at night wondering about the nature of reality. Our observable universe in this picture is one such pocket, one bubble in an endlessly frothing sea of inflating space, surrounded by other bubbles, each one a universe in its own right, each one potentially vast, each one potentially with its own galaxies and stars and planets. And here's the thing that makes this genuinely different from Everett's many worlds. These aren't parallel branches of a quantum wave function. These are physically separate regions of space. They're out there, in a sense, at enormous distances from us. Distances so large that the light from those other pocket universes will never reach us, because the space between us is still inflating, still stretching faster than light can cross it. They're real places, made of real space and real energy, but they're permanently beyond our observational horizon. We can never see them, never visit them, never receive any signal from them. This is what cosmologists usually mean when they talk about the multiverse, not quantum branching, but eternal inflation, producing an endless collection of pocket universes, each one born from the decay of the inflaton field in some far-flung region of an ever-expanding inflationary background. It's a staggering picture, and it raises an immediate, obvious question. If we can never observe these other pocket universes, how is this science? How is this any different from philosophy, or speculation, or just making things up? That's a fair question, and physicists argue about it constantly. But before we get into that debate, and we will, I promise, there's another layer to this story that makes it even stranger. Because eternal inflation doesn't just predict many universes. When you combine it with certain ideas from string theory, it predicts that those universes might have different physical laws, different constants of nature, different numbers of spatial dimensions even. And that possibility, that the laws of physics themselves might vary from one pocket universe to another, is where the multiverse idea goes from being merely extravagant to being genuinely revolutionary, or genuinely absurd, depending on who you ask. And to understand why anyone would take that possibility seriously, we need to talk about something called the string theory landscape, and a number that has been called the worst prediction in the history of physics, the cosmological constant, sometimes called lambda, sometimes called vacuum energy, sometimes called the energy of empty space. Whatever name you use, it's the number that tells you how much energy is sitting in every cubic centimeter of apparently empty vacuum. And it's a number that has driven theoretical physicists slightly crazy for the better part of a century. Here's the setup. Quantum field theory, which is our best framework for understanding particles and forces, tells you that empty space isn't really empty. Even in a perfect vacuum, with every particle removed, there are still quantum fields fluctuating. Little ripples of energy popping in and out of existence, virtual particles appearing and annihilating, all of it happening constantly, everywhere. And all of those fluctuations carry energy. So the vacuum itself has an energy density, a baseline hum of energy that fills all of space, just by virtue of space existing. Now, if you sit down and try to calculate how much energy the vacuum should have, based on quantum field theory, you get a number. And then, if you go out and measure how much vacuum energy the universe actually seems to have, which we can infer from the observed rate at which the expansion of the universe is accelerating, you get a very different number. And when I say very different, I mean the theoretical prediction is off by a factor of roughly 10 to the power of 120. That's a 1 followed by 120 zeros. It is, by any reasonable standard, the most spectacularly wrong prediction that any physical theory has ever produced. And it's not because quantum field theory is bad. Quantum field theory makes incredibly precise predictions about all sorts of other things. Predictions that match experiments to 10 or 12 decimal places. It's specifically this one quantity, the energy of the vacuum, where the calculation goes haywire. Think about what that means for a second. We have a theory that works beautifully for almost everything. And then for this one particular number, a number that happens to govern the large-scale fate of the entire universe. It gives an answer that's wrong by 120 orders of magnitude. That's not a small discrepancy. That's not a rounding error. That's the kind of mismatch that tells you something deep is going on that you don't understand. And here's what makes it even more puzzling. The observed value of the cosmological constant is tiny, incredibly, absurdly tiny. But it's not zero. For a long time, many physicists hoped it would turn out to be exactly zero, because zero is a natural number. Maybe some unknown symmetry forces it to vanish, and that would be elegant and satisfying. But in 1998, two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, independently discovered that the expansion of the universe is accelerating. The universe isn't just expanding, it's expanding faster and faster over time. And the simplest explanation for that acceleration is a small, positive cosmological constant. A tiny amount of energy in every cubic centimeter of empty space, pushing everything apart. They won the Nobel Prize for this in 2011, and it completely changed the landscape of theoretical physics, because now you couldn't just hope that lambda was zero. It was small, but it was definitely there, and you had to explain why. So the question becomes, why is the cosmological constant so small? Why isn't it enormous the way the naive quantum field theory calculation suggests? And why does it have this particular tiny value, roughly 10 to the minus 122 in natural units, that happens to allow galaxies to form, stars to burn, planets to coalesce, and eventually, life to emerge? Because here's the thing. If the cosmological constant were much larger, even just a few orders of magnitude larger, the universe would have expanded so rapidly that matter would never have clumped together into galaxies. No galaxies, no stars, no planets, no us. And if it were negative and large, the universe would have collapsed back on itself long ago. The value we observe sits in this incredibly narrow window that permits complex structures to exist, and nobody knows why. This is where the string theory landscape enters the story, and where things get genuinely wild. String theory. And I should say up front that string theory is not a confirmed theory of nature. It's a theoretical framework that's still very much a work in progress. String theory started out in the late 1960s and early 70s as an attempt to describe the strong nuclear force, then got repurposed as a candidate theory of quantum gravity. The basic idea is that the fundamental constituents of nature aren't point-like particles, but tiny, vibrating strings of energy. Different vibration patterns correspond to different particles, the way different vibration patterns on a guitar string produce different notes. It's a beautiful idea, mathematically very rich, and it naturally incorporates gravity in a way that other quantum theories struggle with. But string theory has a peculiar requirement. For the mathematics to be consistent, the strings can't vibrate in just the 3 spatial dimensions we experience. They need extra dimensions. 6 or 7 additional spatial dimensions beyond the 3 we know about. And those extra dimensions have to be curled up, compactified, folded into tiny geometric shapes, so small that we can't detect them directly. The specific shape of those curled-up dimensions matters enormously, because it determines what kind of physics you get in the large dimensions we can see. Different shapes give you different particles, different forces, different constants of nature. The shape of the internal geometry is, in a sense, what selects the laws of physics. Now, for a long time, string theorists hoped that there would be essentially one consistent way to compactify those extra dimensions. One unique shape, one unique geometry, leading to one unique set of physical laws that would turn out to match our universe. That was the dream. You'd start from this elegant mathematical framework, work out the geometry, and out would pop the standard model of particle physics, the correct cosmological constant, the right masses for all the particles, everything. One theory, one solution, one universe. That dream didn't survive. Starting in the early 2000s, work by a number of physicists, Raphael Bousso and Joe Polchinski, published an influential paper in 2000, and then Leonard Susskind really crystallized the picture around 2003, showed that string theory doesn't have one solution. It has an astronomically large number of solutions. Each solution corresponds to a different way of compactifying the extra dimensions, a different shape for the internal geometry, and each one gives you a different set of physical laws, different particle masses, different force strengths, different values of the cosmological constant. The number of distinct solutions is estimated to be something like 10 to the 500. That's not a typo. 10 to the 500 different possible configurations, each one describing a mathematically consistent universe with its own version of physics. Susskind called this vast collection of possibilities the string theory landscape. And it's a landscape in a very specific sense. You can imagine it as an enormously complicated terrain, with mountains and valleys and ridges, where each valley represents a different stable configuration, a different set of physical laws. Our universe, with its particular particles and forces and cosmological constant, sits in one specific valley of this landscape. But there are 10 to the 500 other valleys out there in the mathematics, each one equally valid as far as string theory is concerned. Now, here's where the two big ideas collide. You've got eternal inflation, which we talked about, producing an endless number of pocket universes, and you've got the string theory landscape, which provides an enormous number of different possible physical configurations. Put them together, and you get something remarkable. Each time, a pocket universe nucleates out of the inflating background. Each time, a little bubble of space transitions to a lower energy state and starts expanding and cooling. It doesn't have to land in the same valley of the landscape as our universe. It can land in any of those 10 to the 500 valleys. Different pocket universes get different physics, different values of the cosmological constant, different particle masses, maybe different numbers of large spatial dimensions. The multiverse, in this picture, isn't just a collection of widely separated regions with the same physics. It's a collection of regions with genuinely different laws of nature. And suddenly, the cosmological constant problem looks different. You don't have to explain why the cosmological constant has this one particular tiny value from first principles. Instead, you can say, the cosmological constant takes every possible value across this vast ensemble of pocket universes. Most of those values are huge, and in those universes, nothing interesting happens. Space expands too fast for structures to form, or it collapses too quickly. But in the rare pocket universes where the cosmological constant, happens to fall in that narrow, life-permitting window, observers can exist. Observers who look around and measure the cosmological constant and find it to be small. Not because there's some deep mechanism forcing it to be small, but because they couldn't exist anywhere else. This is the anthropic argument, and it's one of the most controversial ideas in all of modern physics. The person who really brought this reasoning into sharp focus, at least in the context of the cosmological constant, was Steven Weinberg. And the timing is remarkable. In 1987, more than a decade before the discovery that the universe's expansion is accelerating, Weinberg published a paper in which he argued that if you assumed the cosmological constant could take a range of values across different regions of the universe, then anthropic reasoning would predict that observers like us should measure a value that's small but not zero. He even estimated roughly how small it should be, and his estimate turned out to be in the right ballpark when the actual measurement came in 11 years later. That's a striking piece of reasoning, whether you find it satisfying or maddening, and people do find it maddening. Many physicists absolutely hate the anthropic argument. They see it as giving up, as abandoning the search for a fundamental explanation and replacing it with what amounts to a selection effect. It feels, to its critics, like saying, things are the way they are because if they weren't, we wouldn't be here to notice. Which is true, but doesn't feel like it explains anything. It feels circular. It feels like the end of physics rather than the beginning of a deeper understanding. But its defenders, and they include serious, accomplished physicists like Susskind, Busso, and Weinberg himself, argue that this reaction is emotional, not logical. They point out that selection effects are a perfectly legitimate part of science. We don't find it mysterious that we live on a planet with liquid water, even though most of the universe is inhospitable to life. We don't demand a fundamental theory that predicts the Earth's exact distance from the Sun. We just note that we couldn't exist on Mercury or Neptune, so of course we find ourselves on a planet in the habitable zone. The anthropic argument about the cosmological constant is, they say, the same kind of reasoning applied on a much grander scale. The multiverse is the ensemble, and we're in the pocket universe that permits our existence, just as we're on the planet that permits our existence. The debate is fierce, and it's ongoing, and it cuts right to the heart of what we think science is supposed to do. Is a theory scientific if it makes predictions that can't be tested? Is the multiverse a legitimate scientific hypothesis? Or is it metaphysics dressed up in equations? These are questions that reasonable, brilliant people disagree about profoundly, and the answers matter, because they shape what the next generation of physicists decides to work on, what questions they consider worth asking, what they consider a valid explanation. But there's yet another angle to this whole multiverse story that we haven't touched yet, and it comes from a completely different direction. It doesn't involve inflation or string theory at all. It comes from the mathematics of quantum mechanics itself, from something called decoherence, and the modern understanding of what happens when a quantum system interacts with its environment. And this thread loops us all the way back to Hugh Everett and the many worlds interpretation, but with a much more sophisticated understanding than Everett had in 1957. Because in the decades after Everett's thesis was largely ignored, a quiet revolution was happening in the foundations of quantum mechanics, driven by people who were asking a deceptively simple question. If quantum mechanics says that particles can be in superpositions, in multiple states at once, then why does the world we actually experience always look definite? Why do we never see a cat that's both alive and dead? And the answer that emerged slowly and painstakingly, starting in the 1970s and really coming together in the 80s and 90s, has a name that sounds almost technical, almost clinical, but the idea behind it is anything but dry. That name is decoherence. And understanding decoherence is, I think, one of the most important keys to making sense of why the many worlds interpretation went from being this obscure, almost embarrassing footnote in physics to something that a huge number of serious physicists now consider the most elegant and natural reading of quantum mechanics. So let's talk about what decoherence actually is, because it answers that nagging question, the one that bothered people from the very beginning of quantum theory. You've got an electron that can be in a superposition of spinning clockwise and spinning counterclockwise at the same time. Fine. Quantum mechanics says so, and every experiment confirms it. But then you look at a baseball, which is made of electrons and protons and neutrons, and the baseball is never in two places at once. It's always right there, in your hand, or flying through the air, doing one definite thing. So where does the weirdness go? Where's the boundary between the quantum world and the classical world? The Copenhagen interpretation, remember, just sort of drew a line and said, well, when you measure something, the wave function collapses, and you get a definite result. But it never really explained what a measurement is, or why measurement should be special, or where exactly that line sits. It was a pragmatic answer, not a deep one. The person who really got the ball rolling on decoherence was a German physicist named Heinz-Dieter Zeh. In 1970, Zeh published a paper that was, frankly, ahead of its time. He pointed out something that seems obvious in hindsight, but was genuinely radical at the time. Quantum systems in the real world are never truly isolated. They're always interacting with their environment, with air molecules, photons, the vibrations of whatever apparatus you're using. And those interactions matter enormously. Zeh argued that when a quantum system becomes entangled with its environment, and we'll unpack what that means, the superposition doesn't disappear, but it becomes effectively invisible. The interference effects that make quantum mechanics so strange, the ability of different possibilities to interact with each other, those get smeared out and lost into the environment so quickly and so thoroughly that for all practical purposes, you're left with something that looks classical, something that looks like a definite outcome. Now here's the thing. Zeh's paper was not well received. In fact, it was largely ignored or dismissed. The foundations of quantum mechanics were not considered a respectable thing to work on in the 1970s. If you were a serious physicist, you did particle physics, or condensed matter or astrophysics. You didn't sit around worrying about what wave function collapse really meant. That was philosophy, not physics. And Zeh was somewhat isolated, working at the University of Heidelberg, pushing ideas that most of his colleagues thought were a waste of time. It's one of those stories that repeats itself in science. The person asking the right question at the wrong time, in the wrong institutional context. But the idea didn't die. It was picked up and developed much more rigorously in the 1980s by Wojciech Zurek, a Polish-American physicist working at Los Alamos National Laboratory. Zurek gave the framework a more complete mathematical treatment and coined some of the key terminology that people still use today. He talked about how the environment effectively monitors a quantum system, continuously extracting information about it, and the specific states that survive this environmental monitoring, the states that are robust against decoherence, he called pointer states. Think of that name. Pointer states. Like the pointer on a measuring instrument that points to a definite reading. The environment selects certain states as stable, as the ones that persist, and it's those states that correspond to what we experience as classical reality. Let me try to make this more concrete, because it's one of those ideas that sounds abstract until you see how it works. Imagine you have a tiny particle, an electron, say, and it's in a superposition of being in two different locations, left and right. Now, in a perfect vacuum, completely isolated from everything, that superposition persists. The electron is genuinely in both places, and the two possibilities can interfere with each other, creating those beautiful interference patterns that quantum mechanics is famous for. But now, put that electron in a room full of air. What happens? Air molecules start bouncing off it. And here's the crucial part. The air molecules that bounce off the electron when it's on the left travel in different directions than the ones that bounce off it when it's on the right. So the air molecules become entangled with the electron's position. The information about where the electron is leaks out into the environment, gets spread across billions and billions of air molecules. And once that happens, the interference between the left and right possibilities becomes astronomically small. Not zero, technically, but so unimaginably tiny that no experiment could ever detect it. The superposition is still there in the full mathematical description of the electron plus all the air molecules, but for any practical observation of just the electron, it looks like the electron is in one place or the other. It looks classical. And this happens fast. Unbelievably fast. Zurich and others calculated the decoherence timescales for everyday objects, and the numbers are staggering. For something the size of a dust grain floating in air at room temperature, the time it takes for quantum superpositions to become undetectable is something like 10 to the minus 31 seconds. That's a trillionth of a trillionth of a billionth of a second. For a bowling ball, it's even faster. You can't even define a meaningful interval of time that short. So the reason you never see a cat that's both alive and dead, the reason baseballs don't quantum tunnel through walls, isn't that there's some mysterious collapse mechanism that kicks in at a certain size. It's that big objects interact with so many environmental particles so quickly that their quantum behavior becomes invisible almost instantaneously. The classical world isn't a separate realm with different rules. It's what quantum mechanics looks like when decoherence has done its work. Now, you might be thinking, okay, that's neat, but does decoherence solve the measurement problem? Does it tell us what actually happens? And this is where it gets really interesting and really subtle. Because decoherence by itself doesn't tell you that only one outcome occurs. It tells you that the different outcomes stop interfering with each other. It explains why you don't see superpositions. But it doesn't explain why you see one particular result rather than another. If you're a Copenhagen person, you might say, great. Decoherence explains why collapse looks the way it does. And then collapse still happens on top of that. But if you're an Everettian, if you take the many worlds view, decoherence gives you something even more powerful. It gives you the mechanism by which worlds branch. Think about what decoherence is really saying. When a quantum system interacts with its environment, and the different possibilities become entangled with different environmental states, those possibilities can no longer communicate with each other. They can't interfere. They're dynamically independent. From the perspective of an observer entangled with one branch, the other branches are completely inaccessible. They might as well not exist. And this is exactly what the many worlds interpretation needs. It needs a way to explain why. If all outcomes happen, we only experience one. Decoherence provides that explanation. The branches don't disappear. They decohere. They become separate, non-interacting threads of reality, each one containing observers who see a definite outcome and have no access to the other branches. This is why the many worlds interpretation experienced a genuine renaissance starting in the late 80s and 90s. It wasn't just Everett's original idea anymore. It was Everett's idea plus decoherence, and together they told a much more complete and compelling story. The wave function of the universe never collapses. It just keeps evolving according to the Schrödinger equation, the one equation that everyone agrees on. And decoherence explains why this continuous, unitary evolution produces the appearance of a classical world with definite outcomes. You don't need to add collapse as an extra postulate. You don't need to draw an arbitrary line between the quantum and classical realms. You just need quantum mechanics itself, applied consistently to everything, including observers and measuring devices and the environment. And this is where someone like David Deutsch enters the story. Deutsch, an Oxford physicist, became one of the most prominent and passionate advocates for the many worlds interpretation starting in the 1980s. But he didn't just argue for it philosophically. He showed that taking many worlds seriously could lead to new physics, new ideas. In 1985, Deutsch published a landmark paper laying out the theoretical foundations of quantum computing. And his motivation was explicitly many-worldish. He argued that a quantum computer works by performing computations across multiple branches of the multiverse simultaneously. When you run a quantum algorithm, you're harnessing the parallelism of the multiverse itself. Now, not everyone agrees with that particular interpretation of quantum computing. You can describe quantum computation without invoking many worlds, but Deutsch's point was that the many worlds picture made quantum computing intuitive. It made it obvious that quantum computers should be more powerful than classical ones because they have access to more computational resources, the resources of parallel branches. And quantum computing is real. It's not science fiction. Companies and governments are spending billions of dollars building quantum computers right now. The basic principles work. Qubits can be in superpositions, and quantum algorithms like Shor's algorithm for factoring large numbers are exponentially faster than any known classical algorithm. Whether you describe that speed-up as happening because of many worlds or because of some other interpretation of quantum mechanics, the speed-up itself is an empirical fact. And Deutsch would say, if you want the most natural, most explanatory account of why quantum computers work, many worlds gives it to you. But let's come back to the philosophical tension, because it's real and it's important. The many worlds interpretation, even with decoherence, faces serious objections. And the most significant one, the one that keeps philosophers and physicists up at night, which is fitting given that you're hopefully drifting off, is the problem of probability. Here's the issue. In standard quantum mechanics, when you measure an electron that's in a superposition of spin-up and spin-down, you might get spin-up with probability 70% and spin-down with probability 30%. Those probabilities are the bread and butter of quantum mechanics. They're what let you make predictions. They're what experiments confirm. But in many worlds, both outcomes happen. There's a branch where you see spin-up and a branch where you see spin-down. So what does it even mean to say one outcome is more probable than another, if both outcomes definitely occur? This is not a trivial question. It's arguably the hardest problem in the foundations of quantum mechanics, and people have been wrestling with it for decades. Deutsch himself took a crack at it using decision theory, the mathematics of rational choice, to argue that a rational agent who believes in many worlds should behave exactly as if the standard quantum probabilities apply. The idea is that even though both branches exist, you should care more about branches with higher quantum weight, in the same way that you care more about outcomes with higher probability in ordinary life. David Wallace, another Oxford philosopher-physicist, extended this argument in the 2000s into a much more rigorous framework. Their claim is that the Born rule, the rule that tells you how to calculate quantum probabilities from the wave function, can be derived from many worlds plus rational decision-making, rather than being assumed as a separate postulate. Not everyone buys it. Critics argue that the whole approach is circular, that you're smuggling probability in through the back door by assuming that branch weight should matter. The debate gets technical and philosophical in equal measure, and it's one of those arguments where both sides have genuinely strong points. But here's what's remarkable. The fact that this debate is happening at all in serious academic journals, among serious physicists and philosophers, tells you how far many worlds has come from the days when Everett's thesis was a curiosity and Bryce DeWitt had to practically drag it into the spotlight. And there's another thread to this story that weaves through everything we've been talking about. A thread about information, about what information is in a quantum mechanical universe, and about a paradox involving the most extreme objects in the cosmos. Because in the 1970s, right around the time Zay was thinking about decoherence, Stephen Hawking dropped a bombshell on theoretical physics that would take nearly 50 years to fully resolve, and the resolution, or at least the leading candidate for a resolution, ties together quantum mechanics, gravity, and the multiverse in ways that nobody saw coming. So let's talk about it. In 1974, Stephen Hawking published a paper that, on the surface, seemed like a straightforward calculation. He applied quantum field theory to the curved spacetime around a black hole, and what he found was that black holes aren't actually black. They radiate. They glow faintly with thermal radiation, what we now call Hawking radiation. The temperature is incredibly low for any black hole you'd actually find in nature. A black hole with the mass of our sun would have a temperature of about 60 billionths of a Kelvin, which is so cold it makes the cosmic microwave background look like a furnace. But the point isn't the temperature. The point is that the radiation exists at all, because if a black hole is radiating, it's losing energy. And if it's losing energy, it's losing mass. And if it's losing mass, then given enough time, an almost incomprehensibly long time, but a finite time, the black hole will evaporate completely. It will shrink and eventually just vanish. And that's where the problem starts. Because think about what went into that black hole over its lifetime. Stars, gas, dust, maybe entire planets. All of that stuff was made of particles, and those particles had specific quantum states. There was information encoded in them, information about what they were, how they were arranged, what their quantum properties were. Now, Hawking's calculation showed that the radiation coming out of the black hole is thermal. It's random. It's like the static on a dead television channel. It carries no information about what fell in. So when the black hole finally evaporates completely, where did all that information go? It seems to have been destroyed. And here's why that's a crisis. In quantum mechanics, information is never destroyed. Ever. This isn't just a preference or a convention. It's built into the mathematical structure of the theory. Quantum mechanics is what physicists call unitary, which means that the evolution of a quantum system is always reversible. If you know the complete quantum state of a system at any time, you can in principle reconstruct its state at any earlier time. It's like a movie that you can always play backward. Destroying information would violate unitarity, and violating unitarity would break quantum mechanics at its foundations. So Hawking was essentially saying, either quantum mechanics is wrong, or our understanding of black holes is wrong, or something very strange is happening that we don't understand yet. Hawking himself, at least initially, was willing to bite the bullet. He argued that black holes really do destroy information, and that quantum mechanics needs to be modified in the presence of gravity. This was a bold claim, and it put him directly at odds with most of the rest of the theoretical physics community. The person who pushed back hardest was Leonard Susskind, the same Susskind we talked about earlier, the one who championed the string landscape. Susskind, along with Gerard 't Hooft, the Dutch Nobel laureate, argued that information must be preserved. They didn't know exactly how, but they were convinced that unitarity was sacred, that you couldn't just throw it away. This disagreement became one of the great intellectual rivalries in modern physics. Hawking and Susskind went back and forth for decades. Susskind later wrote a whole book about it called The Black Hole War, and he described it not as a polite academic disagreement, but as a genuine battle over the soul of physics. Because the stakes were enormous. If Hawking was right and information could be destroyed, then the predictive power of physics itself was undermined. If Susskind was right, then there had to be some mechanism, some way that the information gets out of the black hole, encoded in the Hawking radiation in a way that Hawking's original calculation missed. Now, here's where this connects to everything we've been talking about. One of the key ideas that emerged from this debate is something called the holographic principle. 't Hooft proposed it in 1993, and Susskind gave it a more precise formulation shortly after. The holographic principle says that all the information contained in a volume of space can be described by a theory that lives on the boundary of that space. Think about that. It's saying that a three-dimensional region, everything inside it, every particle, every interaction, can be fully encoded on its two-dimensional surface. Like a hologram, where a flat piece of film contains all the information needed to reconstruct a three-dimensional image. The name is almost too perfect. This sounds abstract, but it got spectacularly concrete in 1997, when Juan Maldacena, a young Argentine-American physicist working at Harvard, published what might be the most influential paper in theoretical physics in the last 30 years. Maldacena showed that there is an exact mathematical equivalence, a duality, between a specific type of gravitational theory in a five-dimensional space called anti-de Sitter space and a quantum field theory without gravity living on the four-dimensional boundary of that space. This is called the ADS/CFT correspondence, and it's one of those results that sounds impossibly technical, but has an absolutely profound implication. Gravity in the interior is equivalent to quantum mechanics on the boundary. They're not just similar, they're the same theory, written in two different languages, and this matters for the information paradox because it strongly suggests that information is preserved. If everything happening inside the space, including black holes forming and evaporating, is equivalent to a perfectly unitary quantum theory on the boundary, then information can't be lost. The boundary theory is quantum mechanical, and quantum mechanics preserves information. Period. The information must get out somehow. Maldacena's paper has been cited over 20,000 times. It launched an entire subfield, and it gave physicists a powerful tool for studying quantum gravity, even though we still don't have a complete theory of quantum gravity in our actual universe. See, here's the catch. Our universe doesn't have anti-de Sitter geometry. Our universe has a positive cosmological constant, which means it's closer to what's called de Sitter space. And the ADS/CFT correspondence doesn't straightforwardly apply to de Sitter space. So we have this beautiful, precise, mathematically rigorous result that works perfectly in a universe that isn't quite ours. It's like having a perfect map of a neighboring country. Incredibly useful, deeply suggestive, but you can't just assume every road matches up. Still, the lessons from ADS/CFT have reshaped how physicists think about the multiverse, about space-time, about what reality fundamentally is. Because if the holographic principle is right, if a lower dimensional boundary theory can encode everything about a higher dimensional bulk, then space-time itself might not be fundamental. Space-time might be emergent. It might be something that arises from more basic quantum information, the way temperature arises from the motion of molecules. You don't find temperature in any individual molecule. It's a collective property. And space-time might be the same kind of thing, not a stage on which physics happens, but a consequence of physics happening. This idea has been developed extensively by people like Mark van Ramsdonk at the University of British Columbia, who published a beautiful paper in 2010 arguing that quantum entanglement is the glue that holds space-time together. The argument goes roughly like this. Take two quantum systems that are entangled, and the ADS/CFT correspondence tells you that they correspond to two regions of space-time that are connected. Reduce the entanglement, and the regions pull apart. Remove the entanglement entirely, and the space-time pinches off. The connection is severed. Entanglement builds geometry. That's a staggering claim, and it's still being worked out, but it's taken seriously by a large and growing community of physicists. And you can start to see how this loops back to the multiverse, right? If space-time is built from quantum entanglement, and if the many worlds interpretation says that the universal wave function contains all these branches, all these different outcomes, all entangled with each other in specific ways, then what does the geometry of that total wave function look like? Could different branches correspond to different spacetimes? Could the multiverse of many worlds and the multiverse of eternal inflation be two descriptions of the same underlying quantum structure, seen from different angles? These are questions people are actively working on right now. They're not settled. They're not even close to settled. But the fact that they can be formulated precisely, that there are mathematical tools to attack them, that's new. That's a development of the last 20 or so years, and it comes directly from the collision of quantum mechanics and gravity that Hawking triggered with his 1974 paper. There's one more twist in the black hole information story that's worth mentioning, because it shows how alive and contentious this field still is. In 2012, 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, often referred to by their initials as AMPS, published a paper arguing that the standard picture of black holes harbored a deep contradiction. They showed that 3 things physicists believed about black holes couldn't all be true simultaneously. That information is preserved, that nothing dramatic happens when you cross the event horizon, and that physics outside the black hole obeys standard quantum field theory. You can have any 2, but not all 3. And if you give up the smooth horizon, what you get instead is something they called a firewall. A wall of high-energy radiation right at the event horizon that would incinerate anything falling in. This was shocking. The whole point of general relativity's equivalence principle is that you shouldn't notice anything special at the horizon. Falling into a large black hole should feel like floating in empty space, at least locally. A firewall would violate that, and violating the equivalence principle would mean modifying general relativity in a fundamental way. The firewall paradox set off a firestorm, no pun intended, of debate that's still ongoing. Susskind weighed in, Maldacena weighed in, Hawking himself proposed a radical alternative shortly before his death in 2018, suggesting that black hole horizons might be far more complex and chaotic than anyone imagined. And here's what I find so fascinating about all of this. The black hole information paradox started as a thought experiment about an exotic astrophysical object, but pursuing it relentlessly for 50 years has led physicists to question the nature of space-time itself, to discover deep connections between entanglement and geometry, and to develop tools that might eventually tell us whether the multiverse is real and what it even means for it to be real. The deepest questions in physics have a way of converging, of turning out to be the same question asked in different languages. Which brings us to something we haven't really addressed yet, something that's been lurking in the background of every multiverse idea we've discussed: the question of whether any of this is actually science. Because there's a serious, legitimate, important criticism of multiverse theories that goes like this. If you can't observe the other universes, if you can't test for their existence, if the theory predicts everything and therefore predicts nothing specific, then how is it science at all? And that's not a question coming from people who don't understand physics. It's coming from some of the sharpest minds in the field, people who care deeply about the integrity of the scientific enterprise. So let's sit with that for a while, because it deserves a thoughtful answer, or at least a thoughtful exploration, since the honest truth is that the physics community hasn't fully settled this one yet. The person most associated with this critique is probably Paul Steinhardt, who's a theoretical physicist at Princeton. And here's what makes his criticism sting. Steinhardt wasn't some outsider throwing rocks. He was one of the original architects of inflationary theory back in the early 1980s. He worked alongside Alan Guth and Andre Linde in developing the very framework that eventually led to eternal inflation and the idea of pocket universes. So, when Steinhardt says that the multiverse has taken inflation in a direction that's scientifically problematic, it carries real weight. He's not dismissing something he doesn't understand. He's rejecting something he helped build, and that kind of intellectual honesty is worth paying attention to. His argument, stripped down to its core, goes something like this. A good scientific theory makes predictions that could, in principle, be wrong. That's Karl Popper's falsifiability criterion, and it's been a cornerstone of the philosophy of science since the mid-20th century. The idea is simple and powerful. If your theory is compatible with every possible observation, then it doesn't actually tell you anything about the world. It's not that the theory is necessarily wrong. It's that it's not even playing the game of science. And the multiverse, Steinhardt argues, falls into exactly this trap. If there are 10 to the 500 different possible universes in the string landscape, each with different physical constants, different particle masses, different forces, well, then whatever we observe in our universe, the multiverse can accommodate it. The cosmological constant is small. There's a pocket universe for that. The electron mass is what it is. There's a pocket universe for that too. You can never be surprised because the theory has an answer for everything, which is really the same as having an answer for nothing. Now, that's a powerful objection. And if you've been following along through all the ideas we've explored, many worlds branching, eternal inflation, the string landscape, the anthropic principle, you might feel the force of it. There's something unsatisfying about a framework that seems to explain everything after the fact, but doesn't stick its neck out and tell you something specific before you go. Look. But here's the thing. The defenders of the multiverse have responses, and they're not trivial. Let's walk through a few of them, because this debate is genuinely one of the most important conversations happening in fundamental physics right now. The first response is historical, and it's actually pretty compelling. Remember Steven Weinberg's prediction about the cosmological constant? We talked about that a while back. In 1987, Weinberg used anthropic reasoning, which is essentially multiverse reasoning, to predict that the cosmological constant should be small but not zero, roughly within a couple of orders of magnitude of the value needed for galaxies to form. And then, in 1998, when Saul Perlmutter, Brian Schmidt, and Adam Rees discovered that the expansion of the universe is accelerating, the measured value of the cosmological constant landed almost exactly where Weinberg said it would. That's a prediction. A real, quantitative, ahead-of-time prediction that came out of multiverse-style thinking and was confirmed by observation. So you can't quite say the multiverse predicts nothing. At least in this one case, it predicted something specific, and it was right. Now, critics will push back and say, one successful prediction doesn't validate an entire framework, and that's fair. But it does complicate the simple narrative that multiverse theories are inherently unfalsifiable. They can, under certain conditions, generate testable predictions. The question is whether they do so reliably enough and broadly enough to count as a proper scientific program. The second defense is more subtle, and it has to do with what we mean by observation. When people say you can't observe other universes, that's true in the most direct sense. You can't point a telescope at another pocket universe or detect the branching of an Everettian world. But science has always dealt with unobservable entities. You can't directly observe quarks. You can't see an electron's wave function. You've never touched a gravitational field. What you observe are the consequences of these things, the indirect signatures they leave in data you can collect. And some physicists argue that the multiverse could leave indirect signatures too. For example, in eternal inflation, if our pocket universe nucleated close to another pocket universe in the very early moments of cosmic history, the two bubbles might have collided. And a bubble collision would leave a specific, detectable pattern in the cosmic microwave background. A circular bruise, essentially, with a particular temperature profile. In 2011, a team including Matthew Kleben and others actually searched the CMB data from the WMAP satellite for exactly these signatures. They didn't find a convincing detection, but the point is that they could look. The search was scientifically meaningful. There was a prediction, there was a method, and there was data. That's science, even if the result was null. And future experiments with better sensitivity might find something, or might rule out certain versions of eternal inflation with enough confidence to matter. Similarly, in many worlds' quantum mechanics, the theory doesn't just say, other branches exist, and that's it. It makes the same predictions as standard quantum mechanics for every experiment we can perform in our branch. The interference patterns, the entanglement correlations, the decoherence timescales, all of these are testable, and many worlds must get them right to remain viable. Where many worlds differs from Copenhagen is in interpretation, in what the math means, not in what the math predicts for any given experiment. So the question becomes, is it legitimate science to have two theories that make identical predictions for all observable quantities, but differ in their ontology, in what they say exists? that's really a question about the philosophy of science, not physics itself, and reasonable people disagree. And this is where the conversation gets genuinely interesting, because it forces us to ask what science is for. Is it only about making predictions, or is it also about building a coherent picture of reality? David Deutsch, who we talked about earlier, the quantum computing pioneer and passionate many worlds advocate, argues strongly for the latter. He says that explanatory power matters, that a theory which gives you a unified, coherent account of why the world is the way it is has scientific value, even if some of its claims can't be directly tested. The history of science is full of examples where theoretical entities were proposed long before they could be observed. Atoms were controversial for decades. The neutrino was postulated in 1930 by Wolfgang Pauli and wasn't detected until 1956. The Higgs boson was predicted in 1964 and confirmed in 2012, 48 years later. So the mere fact that we can't currently test for other universes doesn't automatically mean we never will, or that the idea is unscientific. But, and this is a real but, there's a difference between we can't test this yet and we can't test this in principle. If the other universes in eternal inflation are beyond our cosmic horizon, forever causally disconnected from us, then no amount of technological improvement will ever let us observe them. That's not a practical limitation. It's a fundamental one. And some philosophers of science, like George Ellis at the University of Cape Town, have argued that this puts the multiverse in a genuinely different category from historical cases like atoms or neutrinos. Those things were always in our universe, always interacting with matter we could eventually probe. Other pocket universes, by definition, are not. So where does this leave us? Honestly, in a fascinating and somewhat uncomfortable place. The multiverse isn't cleanly falsifiable in the traditional Popperian sense, but Popper's criterion itself has been debated and refined by philosophers of science for decades. Strict falsifiability, taken to its logical extreme, would rule out a lot of things most scientists are perfectly comfortable with. What seems to be emerging instead is a more nuanced view, one where the multiverse is evaluated not by a single yes or no test, but by a web of evidence, consistency, and explanatory power. Does it solve real problems? The cosmological constant problem, for instance. The multiverse at least offers a framework for understanding why the constant has the value it does, which is more than any other approach has managed. Does it connect to well-tested physics? The string landscape emerges from string theory, which itself is deeply connected to quantum field theory and general relativity, both spectacularly well confirmed. Does it make any predictions at all? Weinberg's cosmological constant prediction suggests yes, at least sometimes. None of this proves the multiverse is real, but it does suggest that dismissing it as not even science might be too hasty. The truth is probably that we're in a transitional period, a time when our theoretical frameworks have outrun our experimental capabilities, and we're still figuring out the right epistemic standards to apply. This has happened before in physics. It happened with general relativity, which made predictions about gravitational waves that weren't confirmed for 100 years. It happened with quantum mechanics, where the full implications of entanglement weren't experimentally verified until Alain Aspect's experiments in 1982, more than 4 decades after Einstein, Podolsky, and Rosen first raised the issue. And there's one more angle on this that I think is worth mentioning, because it connects back to something deep about how physics works. Remember the holographic principle and ADS/CFT, the idea that a gravitational theory in a volume of space can be completely described by a quantum theory on its boundary? That correspondence, Maldaceno's great insight, has given physicists a new way to think about what it means for different descriptions of reality to be equivalent. Two theories that look completely different, one with gravity, one without, can turn out to be the same theory wearing different clothes. And some physicists have started to wonder whether something similar might be true of the different multiverse concepts themselves. Maybe Everett's branching wave function and Linda's eternally inflating cosmos and the string landscape aren't three separate ideas about three separate multiverses. Maybe they're different mathematical descriptions of the same underlying structure, seen from different vantage points. And that idea, that unification conjecture, is one of the most tantalizing threads in all of modern theoretical physics. Let me try to unpack why some very serious people think this might be true, because it's not just wishful thinking or hand-waving. There's actually a chain of reasoning that connects these dots, and it starts with something we touched on earlier: decoherence. Remember, decoherence is the process by which quantum superpositions become effectively classical. When a quantum system interacts with its environment, the different branches of the wave function lose the ability to interfere with each other. They become, for all practical purposes, separate worlds. That's the Everett picture. Now here's something subtle. In the many worlds interpretation, the branching structure of the wave function has a kind of tree-like geometry. Each measurement, each interaction, creates new branches, and those branches spread out in a pattern that you can describe mathematically. And some physicists have noticed that this branching structure bears a striking resemblance to the geometry of an eternally inflating universe, where bubble universes are constantly nucleating inside a rapidly expanding background. This isn't just a loose analogy. In 2011, a physicist named Yasunori Nomura at Berkeley published a paper arguing that the many worlds of quantum mechanics and the many worlds of eternal inflation are literally the same thing. His argument goes something like this. In eternal inflation, you have this vast inflating space with pocket universes forming inside it. But here's the thing. You can never actually observe all of that space. Any single observer is trapped inside their own pocket universe, causally disconnected from the others. So from any observer's perspective, the other pocket universes are not things you can visit or see. They're like the other branches in Everett's wave function, real in the mathematics, but inaccessible in practice. Nomura's insight was that if you take quantum mechanics seriously, really seriously, then the global description of the eternally inflating multiverse, this God's eye view of all the bubble universes spread out across space, is actually redundant. It's overcounting. The real physical description, the one that avoids double counting, is the quantum wave function as seen by a single observer. And that wave function, with all its branches, already contains everything you need. The many worlds of eternal inflation are the many worlds of quantum mechanics. They're not two separate multiverses. They're one multiverse described in two different mathematical languages. Now, you might be thinking, that sounds like a pretty bold claim. And it is. Not everyone agrees with Nomura's argument by any means. But what's remarkable is that it's not an isolated idea. Around the same time, Leonard Susskind, who you'll remember as one of the architects of the string landscape and the holographic principle, was developing similar ideas from a different direction. Susskind had been thinking about what's called the census problem, or sometimes the measure problem, in eternal inflation. Here's what that is. If you have an infinite number of pocket universes and you want to make predictions about what a typical observer should see, you need some way to count them. You need a measure a mathematical rule for assigning probabilities to different observations. And this turns out to be incredibly tricky. Different measures give different predictions, and there's no obvious way to choose the right one. It's one of the deepest unsolved problems in inflationary cosmology. Susskind realized that this measure problem might actually be telling us something profound. Maybe the reason we can't figure out how to count all the pocket universes from the outside is that the outside view, the global view, isn't physically meaningful. Maybe the only meaningful description is the one from the perspective of a single observer, a single causal patch. And within that causal patch, the different possible histories and the different possible configurations of the universe are just different branches of the quantum wave function. So again, you end up with the same conclusion. The multiverse of eternal inflation and the multiverse of quantum mechanics collapse into a single framework. And here's where the string landscape fits in. Remember, the landscape is this vast space of possible vacuum states, roughly 10 to the 500 different ways the extra dimensions of string theory can be curled up, each one corresponding to a different set of physical laws. In eternal inflation, different pocket universes can settle into different vacuum states, so the landscape populates itself naturally. But if Nomura and Susskind are right, then the landscape isn't really a collection of separate universes scattered across physical space. It's more like a collection of possible states in the quantum wave function. Different branches correspond to different vacuum states, and the branching process, decoherence, is what makes them distinct. The landscape becomes a quantum landscape, a space of possibilities within a single wave function rather than a map of physically separated regions. Think about what that means for a second. Instead of three confusing multiverse concepts that seem unrelated, you might have one underlying reality that looks different depending on how you describe it. If you describe it in the language of cosmology, you see eternal inflation with bubble universes. If you describe it in the language of quantum mechanics, you see Everett branches. If you describe it in the language of string theory, you see the landscape of vacua. Three perspectives, one elephant. It's the blind men and the elephant, except the blind men are some of the smartest physicists who have ever lived, and the elephant is the fundamental structure of reality. Now, I want to be really honest with you here, because this is speculative. This is frontier physics, the kind of thing that might turn out to be brilliantly correct or might turn out to be a beautiful dead end. We don't have a complete mathematical framework that fully unifies these three pictures. What we have are suggestive arguments, partial results, and a growing sense among some theorists that the connections are too deep to be coincidental. But it's not proven, it's not settled. It's the kind of thing that physicists argue about at conferences and in late-night conversations, and it might take decades to resolve. But even if the full unification conjecture doesn't pan out, the individual pieces have already taught us something extraordinary about the nature of physical theory. A DS/CFT showed us that two radically different-looking theories can be secretly identical. Decoherence showed us that the appearance of a classical world can emerge from quantum mechanics without any special collapse mechanism. The string landscape showed us that what we thought were free parameters of nature might actually be environmental variables, different in different regions of a larger structure. Each of these insights, on its own, changed how physicists think about what a theory of nature should look like. And this brings us to something that I think is genuinely important for understanding where physics is right now in our time, in the early 21st century. We're in an era where the biggest questions aren't necessarily going to be answered by building a bigger collider or a better telescope, though those things certainly help. Some of the biggest questions might be answered by understanding the mathematical structure of the theories we already have more deeply. By finding new dualities, new equivalences, new ways of seeing that what looked like separate problems are actually the same problem in disguise. This is a different kind of physics than what most people picture when they think of the field. Most people think of experiments, Galileo dropping balls from the Tower of Pisa, Rutherford scattering alpha particles off gold foil, the discovery of the Higgs boson at the Large Hadron Collider. And experiments are absolutely central to physics. They always have been, and they always will be. But there have also been periods in the history of physics where the biggest advances came from theoretical insight, from someone sitting with a pencil and paper, and realizing that the mathematics was trying to tell them something they hadn't been listening to. Einstein's general relativity was like that. Dirac's prediction of antimatter was like that. He looked at an equation and saw that it had solutions with negative energy, and instead of throwing those solutions away, he took them seriously, and it turned out they described a whole new kind of particle that nobody had ever seen. The positron was discovered experimentally a few years later, in 1932, by Carl Anderson, and Dirac's faith in the mathematics was vindicated. So when theorists today look at the mathematics of quantum mechanics, string theory, and cosmology, and see these deep structural connections between different kinds of multiverses, they're doing something that has a long and honorable tradition in physics. They're listening to what the math is trying to tell them. They might be wrong. The math might be misleading them, the way it has sometimes misled people before. But they might also be glimpsing something real, something that future generations will look back on as the moment when the fog started to clear. And there's one more development I want to tell you about, because it's relatively recent, and it connects to almost everything we've talked about. It has to do with quantum information theory, the same field that David Deutsch helped pioneer with his work on quantum computing, and its unexpected relationship to the structure of space-time itself. We talked earlier about how Van Ramsdonk showed that entanglement and space-time geometry are deeply connected, how if you reduce the entanglement between two regions, the geometric connection between them, the spatial bridge, gets thinner and eventually breaks. Well, in the years since that initial insight, a whole community of physicists has been building on it, developing what's sometimes called the IT from qubit program. The name is a play on John Wheeler's famous phrase, it from bit, which suggested that the physical world, the it, might ultimately be built from information, the bit. The it from qubit version updates this for the quantum age, suggesting that space-time itself emerges from quantum entanglement from qubits. One of the key figures in this program is a physicist named Patrick Hayden, along with collaborators like John Preskill, Alexei Kitaev, and many others. And what they've been finding is that the tools physicists developed to understand quantum error correction, the methods for protecting fragile quantum information from noise and decoherence, turn out to be the same mathematical tools you need to describe how the interior of a black hole is encoded in its surface. Think about that for a second. Quantum error correction was invented for engineering purposes. People like Peter Shor and Andrew Steen developed these codes in the mid-1990s, because if you ever want to build a working quantum computer, you need a way to protect your qubits from the constant interference of the outside world. Every stray photon, every tiny vibration, every thermal fluctuation threatens to destroy the delicate quantum states your computer is working with. So you encode your information redundantly, spread it across many physical qubits in clever patterns so that even if some of them get corrupted, the essential information survives. It's conceptually similar to how your phone can still play a scratched audio file, or how a QR code still works even when part of it is damaged. Redundancy protects information. Now here's the wild part. In 2014 and 2015, a physicist named Ahmed Almhiri, the same Almhiri from the AMPS firewall paradox, remember him, along with Shidong and Daniel Harlow, showed that the way information about the interior of a black hole is encoded in the degrees of freedom on its boundary is mathematically identical to a quantum error-correcting code. The geometry of space-time inside the black hole is a kind of encoded message, and the encoding scheme is the same kind of scheme that quantum computing engineers use to protect information in their machines. The bulk of space-time, the interior, is the encoded message. The boundary, the surface, is where the physical qubits live. And the reason you can't easily access the interior information by making simple measurements on the boundary, the reason the holographic dictionary is so complicated, is precisely because the information is protected by this error-correcting structure. Let that sink in. The reason space-time has the properties it does, the reason it's robust, the reason small perturbations on the boundary don't immediately destroy the geometry of the interior, it's because space-time is a quantum error-correcting code. Nature isn't just using the same math that quantum computing engineers stumbled upon. Nature got there first, by about 14 billion years. The universe has been running quantum error correction since the beginning, and we only just figured out what it was doing. This result, which Harlow and collaborators developed further over the next several years, connects to the holographic principle we talked about, to Maldaceno's ADS/CFT correspondence, to the information paradox, to the firewall problem. It touches almost everything. And it suggests something profound about the nature of reality. If space-time geometry emerges from entanglement, and if that emergence follows the logic of quantum error correction, then space itself, the thing you're lying in right now, the distance between your pillow and the ceiling, the gap between Earth and the Moon, all of that might be a consequence of how quantum information is organized. Space isn't the stage on which physics happens. Space is what physics looks like when quantum information is structured in a particular way. And here's where it circles back to the multiverse. Because if space-time emerges from quantum mechanics rather than the other way around, then the question of whether other universes exist out there, somewhere in space, is the wrong question. It's like asking what's north of the North Pole. The question assumes that space is the fundamental thing, that existence means having a location. But if space itself is emergent, if it's a derived property of a deeper quantum description, then the different branches of the quantum state, ever its many worlds, don't need to be somewhere. They're different configurations of the underlying quantum information, and each configuration generates its own emergent spacetime. They're not parallel sheets floating in some higher dimensional space. They're different ways the qubits can be organized, each one giving rise to its own geometry, its own distances, its own sense of here and there. This is why Nomura's unification picture, the one we talked about where many worlds branching and eternal inflation's pocket universes turn out to be the same thing, fits so naturally into the it from qubit framework. If you take the quantum state of the universe seriously, if you don't artificially collapse it, then the full quantum state contains all these branches. Each branch looks, from the inside, like a universe with its own space-time geometry. Some branches might have the geometry of our observable universe. Others might have different geometries, different effective laws of physics, corresponding to different solutions in the string landscape. The multiverse, in this picture, isn't a speculative add-on. It's what you get when you take quantum mechanics and gravity seriously together. Now, I want to be really honest with you here, because we're getting close to the end of this whole journey, and honesty matters. Everything I just described, the It from Qubit program, the connection between error correction and space-time, the unification of different multiverse concepts. This is cutting-edge research. It's beautiful, it's mathematically compelling, and a lot of very smart people believe it's pointing in the right direction. But it is not settled science. We do not have experimental confirmation. We do not have a complete theory of quantum gravity. We have strong hints, deep mathematical connections, and a growing body of theoretical evidence that all seems to point the same way. But pointing and arriving are different things. The honest truth is that as of right now, in the 2020s, we cannot definitively tell you whether the multiverse is real. We can tell you that multiple independent lines of reasoning, from quantum mechanics, from cosmology, from string theory, from black hole physics, from quantum information theory, all seem to converge on the idea that our observable universe is not all there is. We can tell you that the simplest, most economical versions of our best theories naturally produce something multiverse-like. We can tell you that the alternative, insisting that only our observable patch exists, requires adding extra assumptions, extra mechanisms, extra rules to cut off the theories and prevent them from doing what they naturally want to do. And in the history of physics, the version of a theory with fewer arbitrary assumptions has usually turned out to be the right one. Usually, not always. So where does that leave us? Let's step back for a moment and think about what we've actually covered tonight, because it's been quite a journey, and if you've been drifting in and out, that's perfectly fine. That's what this is for. We started with a simple question. What is the multiverse? And we discovered that there isn't one multiverse. There are several different concepts that all get called by the same name, and they come from completely different areas of physics. There's the quantum multiverse, Everett's many worlds interpretation, where every quantum measurement causes the universe to branch. There's the cosmological multiverse from eternal inflation, where our Big Bang is just one bubble in an endlessly inflating sea. There's the string landscape multiverse, where the mathematics of string theory allows something like 10 to the 500th power different possible configurations, each one a potential universe with its own laws of physics. These three ideas were developed independently by different people for different reasons to solve different problems. And yet, and this is the part that I find genuinely breathtaking, recent theoretical work suggests they might all be describing the same underlying reality from different angles. We talked about the people behind these ideas. Hugh Everett, the quiet Princeton graduate student who proposed the most radical reinterpretation of quantum mechanics in history and then walked away from physics when nobody took him seriously. Alan Guth, scribbling spectacular realization in his notebook when he figured out inflation. André Linde, realizing that inflation doesn't just start once, it goes on forever. Juan Maldacena, discovering the holographic principle's most concrete realization and connecting gravity to quantum field theory in a way nobody expected. Leonard Susskind, fighting Stephen Hawking for decades over whether information is destroyed in black holes, and eventually winning. Mark van Ramsdonk, showing that if you remove entanglement, space-time falls apart. All of these people were working on what seemed like separate problems, and bit by bit, thread by thread, their work has been weaving together into something that looks like it might be a single tapestry. We talked about the deep problems that drive all of this, the measurement problem in quantum mechanics. What actually happens when you observe something? The cosmological constant problem. Why is the vacuum energy of our universe so absurdly, preposterously small compared to what our theories predict, and yet not quite zero? The information paradox. Does a black hole destroy information, violating the most fundamental principle of quantum mechanics? The firewall paradox. Can you really fall smoothly through a black hole's event horizon, or does something dramatic happen there? Each of these problems, on its own, is one of the deepest puzzles in physics. And the remarkable thing is that the multiverse concept, in one form or another, keeps showing up as part of the answer. Not because physicists want it to be there. Most of them would prefer a simpler universe. It shows up because the math keeps pointing that way. And we talked about the criticism, which is real and important. The worry that a theory predicting everything predicts nothing. The concern that if you can never observe these other universes, the whole idea isn't really science. These are legitimate concerns, and they've pushed physicists to think much more carefully about what evidence and prediction really mean. Steven Weinberg's prediction of the cosmological constant, made using anthropic reasoning within the multiverse framework, years before it was confirmed by observation, remains one of the most striking examples of a multiverse-motivated prediction that actually came true. It doesn't prove the multiverse exists, but it's hard to ignore. So here you are, lying in the dark, and maybe you're wondering, does any of this really matter to me? My alarm is going to go off in the morning, and I'm going to get up and make coffee and go about my day in what certainly feels like one universe, one solid, reliable, singular universe. And you're right. For all practical purposes, your everyday life unfolds in one branch, one pocket, one configuration. The coffee will taste the same whether or not there are 10 to the 500th power other versions of you drinking slightly different coffee in slightly different kitchens. But here's why I think it matters, even practically, even personally. The history of physics is the history of discovering that the universe is bigger and stranger than we thought. Every time we've made that discovery, that the Earth isn't the center of the solar system, that the solar system isn't the center of the galaxy, that our galaxy is one of hundreds of billions, that the universe itself is expanding. Every single time, it felt disorienting at first, and then eventually, it felt liberating. It expanded our sense of what's possible. It made us more humble and more curious at the same time. And if the multiverse turns out to be real in any of its forms, it would be the biggest version of that same story. Not just billions of galaxies, but billions of universes. Not just a cosmos, but a cosmos of cosmoses. And our particular corner of it, with its specific laws of physics, its specific constants, its specific conditions that allow atoms and stars and planets and people, would be revealed as one extraordinarily specific arrangement out of an almost incomprehensible space of possibilities. There's something strangely comforting about that, I think. Not because it makes us small, although it does, but because it means the universe is so much richer than we can see. It means there's more to reality than what fits inside our light cone, more to existence than what our instruments can detect. The deepest lesson of 20th and 21st century physics might be this: reality is not obligated to be simple enough for us to fully grasp, but it is generous enough to leave us clues. And that's really what all of these physicists have been doing all along. Following the clues. Everett followed the clue that quantum mechanics works perfectly well without collapse if you're brave enough to accept the consequences. Guth and Linde followed the clue that inflation solves so many problems that it's probably true even if probably true, means eternally inflating. Maldacena followed the clue that black holes and quantum field theories share the same information content. Susskind followed the clue that the different corners of theoretical physics keep converging. They followed the clues, not knowing where they'd end up, and they ended up in roughly the same place, looking at roughly the same vast landscape from different vantage points. Whether you're still awake or already drifting, I hope some of this stays with you. Not the details necessarily, but the feeling that the universe is deeply, endlessly interesting, that the smartest people who've ever lived have spent their careers trying to understand it and have barely scratched the surface, and that what they've found so far is more beautiful and more strange than anything they expected. The feeling that right now, as you lie here in the dark, the quantum fields that make up your body are doing their quiet quantum thing, evolving according to the Schrödinger equation, entangled with the world around you in ways that are too complex to ever fully trace. And maybe, just maybe, the universe is branching around you right now, gently and silently, the way it always has, the way it always will, each branch as real as the one you're in. Each one carrying its own version of this quiet night, this breath, this slow slide into sleep. You don't need to decide tonight whether that's true. You don't need to decide anything at all. Just let it be a possibility, one of many, hovering at the edge of your thoughts as they soften and blur. The universe will still be here in the morning, in all its strange and extravagant fullness, waiting for you to wonder about it again.